Hi guys, we're going to focus on linear relationships. In this session, we're going to look at regression, both simple and multiple regression. We'll also take a look at some of the sophisticated modeling techniques that'll help you understand complex relationships. These are fundamental to marketing research, and professional marketing researchers use correlation and regression techniques all the time. And so they're really trying to understand relationships between variables. So does a relationship exist? In what direction does it exist? The strength of the relationship, and then the type. Is it linear or possibly curvilinear? So all that is about covariation. So it's the amount of change in one variable that's consistently related to the change in another variable. So you can think about this degree of association as you would plot out data in the two different variables that when one variable is above its average, if they're positively correlated, then the other variable will be somewhat above its average. If the variables are inversely related, in other words, a negative relationship, then when the first variable is above its average, then the other variable would tend to be below its average. So that is what we're looking at here with covariation. And so when you plot it out with an y-axis, the vertical axis, and the x-axis, you might get a no relationship cloud of points here, like you see on the left-hand side of the screen. But if you get this kind of flattened football here, that's a positive relationship if it's going up to the right. So as the x variable increases, so do the y variables in terms of its size. And then you can also have that football going down to the right. So as x increases, y decreases, it gets smaller. And then you can have this curvilinear relationship where there's this kind of hump in the middle, and you can have relationships that are just inverted. So it looks like a U relationship. So all those are possible relationships. Here's some other possible relationships between two variables. You plot them out. You get no correlation here in the upper left. Then you get a low positive correlation in the upper right. Then you get this high positive correlation in the lower left. Then you get this perfect positive correlation, straight line. And then you get another no correlation, a low negative correlation in the upper right. And then you get a high negative correlation in the lower left. And then you get this perfect negative correlation in the lower right. So as x decreases, as x increases, y decreases by the same amount. You also can have relationships like this. That's this U relationship. And here the measure of association is 0. So basically these relationships between x and y cancel out. So you need to plot out your frequency distribution to see if you have anything like this that might be apparent in your relationships. So the product moment correlation, this is the correlation coefficient. It ranges between negative 1.0, a perfectly negative correlation, to plus 1.0, perfect positive correlation, that 45-degree angle going up to the right that we saw in one of the previous graphs. So assumptions in correlation, you want your data to be interval or ratio scaled in measurement, should have a linear relationship, and this normally distributed population. This is the equation for computing R, which is the Pearson product moment correlation coefficient. And so what we're seeing is basically you're taking the difference for each individual on one variable, X, and you're subtracting the difference in the mean value. So you're subtracting the difference here. And then you're taking another difference on another variable, Y, for that same respondent. And then you're subtracting the overall sample value of Y from that respondent. So you're summing all these cross product terms here. That will produce your numerator. And then down below here, you're doing what we've seen before, which is subtracting the mean value of X from each respondent's value. And then you're squaring that. And then you're also summing that, and as well, you're taking a difference in each respondent's value and the average value, squaring that, summing it, and then you're taking the square root of all of those terms. So let's see how it plays out here. Here we got attitude towards sports cars, duration of car ownership. We have a simple data set here, 12 people, and we'll just designate attitude towards sports cars as X and duration of car ownership Y. So here we get the X bar term 9.33 and the Y bar term, which is the sample value of Y, 6.583. And so we start taking our first cross product term. So we get a value of 10 here, and we subtract its X bar value here, and then we multiply that by the difference of the Y value for that respondent and the overall average value of Y. So that's our first cross product term, and we're going to replicate that for the next respondent who has 12 for X and 9 for Y, 12 for X, 9 for Y, you see here, and we're just going to continue that loop pattern here and summing all those cross product terms until we get this value here of 179.67. This is for our numerator. All right, so we have this difference squared here for our X. So we're summing all these difference terms that are squared. We get 304.67, and we're doing this for Y. We're subtracting the average for Y from each respondent's Y value, squaring those, and then summing that, and then we get 120.92. So here we insert these into the equation here, 304.67, and multiply that by 120.92 and take the square root of it, and then that divides into 179.67, and we get this R value of 0.936. So that is a very strong correlation. And we have to remind ourselves the world is not that round, okay? So we probably rarely see a strong correlation like that. We also want to watch out for spurious correlation. So when we go to Ty Vegan's page here, we can see that there are ridiculous relationships that there's no causal explanation. There's probably a third variable accounting for these, but the distance between Saturn and the sun in these different years, and how many Google searches for how to make a baby. And so we see that the red line is how to make a baby. The black line is distance between Saturn and the sun. It is hard to explain why this relationship might be there. That's a spurious one. So we want to make sure that we're just not illogically moving forward a correlation when it doesn't exist. So here you can see ice cream sales do not cause sunburn. There's some other third variable, which is sunshine, that accounts for probably both of these. That's the causal mechanism, not that ice cream sales make your skin turn red. Okay, so the Pearson correlation coefficient, when we take it to our Santa Fe grill case, likely to recommend is variable X24 and satisfaction is X22. So owners would be interested in this satisfaction or likely to recommend relationship. So we see here that the correlation coefficient is 0.776. So it's when you plot these two variables, they're perfectly correlated with each other, X22 with X22, X24 with X24 here. But then the off-diagonal elements here show you your Pearson correlation coefficient. And the asterisk here means that it is significant at the 0.01 level, and that is a strong correlation. So the correlation does not mean causality. It does mean that there's an association that exists, and it's up to us to determine how important that is. A coefficient of determination, where you square the R term, that gives you this percentage of variation in one variable that it's accounted for in the other variable. So this puts it in a 0 to 100% range and gives you a measure of strength of association. So if we got rankings and we want to see how these two different rankings correlate, and it might be one poll for the top 25 football teams and another poll for the top 25 football teams. So we can see how closely these are correlated. But if we're using ranks like these rankings for top 25 football teams, we'd want to use the Spearman rank correlation coefficient. Here, food quality and service, it looks like it has a minus 0.3 relationship, which would lead us to think about that. Why would we have such a relationship? All right, correlation. Okay, this bivariate regression analysis. Now we're moving into more prediction here. So we can see that there could be a plot of height and weight, those two different variables. And so across individuals, we see that, the taller you are, the more likely it is that you are weighing more. So our square term here is 0.50. And that gives us an understanding of this relationship between height and weight. So we're looking at a least squared procedure and trying to take into account unexplained invariance. So we're trying to fit this line here, and it's the regression line through a cloud of points. And this B, which is the slope of this line, is the beta coefficient that is computed in regression analysis. We'll take a look at that shortly here. If it's a standardized regression, this line will be coming out of the intersection here of y and x, the origin of this plot. If it's an unstandardized regression, it might have an intercept term here, A, that will be used in the regression analysis. So there's a procedure here for doing regression analysis, looking at these scattered diagrams, understanding you have a general linear model you're going to be using, estimating the parameters, obtaining the standardized regression coefficient, looking at the significance for these regression coefficients, and then determining the prediction accuracy of your regression equation. So this is the bivariate regression model. Y equals b sub 0 plus b sub 1 of x. So y is the dependent variable, x is the independent or predictor variable. You got this b sub 0, which is the intercept of the line on the y-axis, and this b sub 1 would be the slope of the x variable. And so it looks like this when we plot it with an error term here. Okay, so the error terms are to be normally distributed, a mean of error, so equally above and below that regression line. And the variance across the range of the x value for the error term is constant. And that these error terms are uncorrelated means that one person enters the data set, one person gets a vote, or their observations, they're not counted more than once. So all these assumptions get plotted out like this. So equal amount of error of these terms above the regression line and below. And you can see these variances are the same across the range of the x variable here. And we have this regression line, b sub 0 plus b sub 1 x. Okay, so that is simple regression. So we have one predictor variable, which is x, and one dependent variable, y. All right, let's see how this plays out in terms of the numbers here. So we have the sum of squares y, which is the amount of total error in the data set here. We're going to look at the sum of squares accounted for by that regression line, which is y hat. And then we have this sum of squares residuals. So it's each y observation minus the slope term for that observation, and then the squared term there. All right, so we see here's our little cloud of data points here. We've got this regression line shooting through here. Y bar is our average value for the dependent variable y. And so we've got this total deviation here. So this is the sum of squares y that we're looking for. But then we got this sum of squares residual, so the deviation explained by the regression line. And then we have this unaccounted for error here. That's deviation not explained by the regression line. And the two variables we'll look at here in our case is duration of residing in a city, so the number of years, and then the attitude toward living in a city. So we see that generally there's a upward line there, so it looks like there's a linear relationship, and it's a positive one. So to determine R squared, we're going to get sum of squares regression and divide that by our total sums of square y. And here we go, sums of square y is the summated term of each of the y terms for our respondents, subtracting the y bar or average for y and squaring that. And then we're going to sum all those sum of squares up to 120.91. So that's our sum of squares y. So we are going to now compute sum of squares regression. So between y bar and that regression line. So that's the y hat minus, for each respondent, minus the y average term for y, squaring that. So we have 6.9763, and we're subtracting the y bar value from each of these and squaring these terms, summing them, and we get our sum of squares regression here of 105.95. And then to get our sum of squares residual, we're going to take each observation and subtract the predicted value here for that term and squaring it, and then we get 14.964. And so 14.964 plus 105.952 is going to give us that value of 120.9168. And so those are the terms that we're using here. So 105.95, the sum of squares regression divided by our total sums of squares y, 120.91 gives the R square value here of 0.8672. So another strong relationship here in the strength of relationship between years lived in a city and predicting the attitude toward the city, which makes sense. Here we see it computed by statistical software. R square is 0.8762. We got our sum of squares regression, 105.95. Our sum of squares residual, 14. And then we are coming here to the mean square terms, and that gives us, leads us to our F value of 70.8.27. So our overall model has a statistical value associated with that F term of 0.00. So it's way out in the right-hand side of that F distribution in the reject region. So we would reject the null hypothesis that the model tells us nothing. It does tell us something, and says there's a relationship here. And our standardized path estimate here for this relationship suggests that the beta term is a strong one, 0.9361. Okay, and there's a t-test associated with that beta term, and that, again, is statistically significant. So we can, with confidence, say that there's a strong relationship between the years you live in a city and the attitude that you have for that city. So it goes up over time. So we've been doing ordinary least squares. We've computed these betas, these small b's, these regression coefficients. And if that beta is large, the variable is a better predictor of y. So going to our Santa Fe Grill application here, we're going to take a look at the relationship between satisfaction, Ch12, a dependent variable, and reasonable prices, X16. So when we put this in the regression model, we see that that F value is large, a statistical significance value of 0.00. So you would reject the null hypothesis that the model tells us nothing or is a crummy fit. And so we can see here that we've got, a R square value of 0.23 and an R value here of 0.479 for this relationship. And so this is when we put in a regression equation, this is our standardized beta coefficient, 0.479. The t-test for this is statistically significant. So we would say that basically you'd get a 0.479 increase in satisfaction for every 1 unit increase for the X variable, which is reasonable prices, X16. And that has face validity. It makes sense. Okay, so R square is this term that we use to determine the strength of relationship. It is this 0 to 100 kind of percentage indicator for strength of relationship. And in social science, even if you get an R square of 0.10, for a psychological variable, which it might be introversion or extroversion, does that relate to some behavior like product purchase? 10% there would be considered a touchdown for psychologists. Probably in multiple regression, you probably want to get 0.4 R square or above so that you're explaining more of the variance for that dependent variable. All right, so some of the multiple regression assumptions is that you have this equal variance across the range of X for your data points. So that would be homoscedastic. But if it's not, you would have maybe some narrowing of the variance in one part of the range and then a widening in another part of the range. You don't want that. A linear relationship, normal distribution, turns out with adequate sample size that the regression technique is robust to departures from these mild departures or moderate departures from these assumptions. So it's durable. So here we're going to take a look at multiple regression. We'll look at the predictors of fresh food taste, food temperature on the dependent variable Ch12 of satisfaction. And looks like our model here is predicting an adjusted R square. This is the term you use when you have multiple indicators. That's your R square term, 0.410. So it adjusts for an inflation in the R square term when you are entering multiple predictors. That statistic here is high, and the significance for that is way low. So we can reject the null hypothesis that the regression model is a crummy fit. And then we look at our coefficients. And we get fresh food has a positive relationship with satisfaction. Excellent food taste, a negative. What? What is this? So, and then proper food temperature, that's positive, but it's not significant. So we have to think about this logically. The worse the food tastes, the more satisfied you are. This just does not ring true, doesn't make sense. So could be an artifact from having particular variables in your equation for regression that are too closely related. And when that happens, the smaller ones in size will tend to flip and take a negative sign. So it's just an artifact of the computational process, and you have to watch for that through your scrubbing of the results. Could that make sense? No, that doesn't make sense. So that must be multicollinearity. So here we can see that when we check this in a binary correlation of Ch12 with X18, excellent food taste, that alone, that relationship is positive 0.393. And so this is the way to check on multicollinearity. So what should you do? Well, the proper approach here would be that you can't include these three variables as predictors. And probably fresh food and excellent food taste are highly correlated. So you need to drop one of these. And it could be fresh food or it could be excellent food taste. They both can't go into your model. They're too closely related. So the relationship here is, let's see, fresh food taste and fresh food is 0.770. So that's too high for inclusion in a regression model. Okay, multiple regression. Here's an example from Lebanon. This is a picture of the geographic footprint of Lebanon with all the religious groups depicted there geographically. It is a checkerboard, and it's multiple checkerboard. So you can see here the purple are Shia, green are Sunni, blue is Druze, red is Maronite, Christian, and they are intermixed. Okay, so a multicultural country for sure. Geographic footprint is a bit smaller than the size of Albany County, Wyoming. However, Lebanon's population in 2026 was estimated to be 5.8 million. Albany County's was 37,000. And oh yes, there's like 1.5 refugees living temporarily in Lebanon. So quite a different scene here. I went there, or I should say, I had partners there collect data about support for sustainable business in Lebanon. And what we found was that there was a relationship here, and using a linear regression, multiple regression approach, that the most important variable here were attitude toward business benevolence. So how philanthropic were businesses, environmental values of customers, how important was protecting the environment to them, and then concern about business ethics. Did businesses actually, were they involved in bribery? And so the more concern they had, the more support there was for sustainable businesses in Lebanon. That was encouraging because we didn't know that before that. Also, just to do face-to-face surveying had not been done because Lebanon was rife with sectarian and political tensions for decades. And our interviewers were the first to go into some of these neighborhoods with a clipboard. It proved to be dicey. Nobody was hurt, but the residents in the neighborhood didn't know who these people were. Were they representing the government, rival religious groups, or even the CIA? So we did get the data, we did get the results, and it turned out to be a methodological contribution by actually obtaining the results from people in those neighborhoods. Here's another less threatening example here, just in terms of workers, commitment to the organization, and then the pay that people receive, the team they're part of, the management they receive, and the work that is there. So here's a depiction of this: the pay, the team, the management, the work, going into commitment, and how does that relate to performance? We'll get back to this. We're depicting here partial least squares, which is a structural modeling relationship technique. It's come out probably in the last 10 years for sure in the marketing academic world. It's valuable for exploration and using small data samples and those that maybe aren't don't align with the assumptions of linear regression. What we have here for Santa Fe Grill, we might say that, yeah, that there's these relationships here, that probably the leading one is the team and how you identify with your team and your commitment to working at that organization. But you can't see the commitment to the organization and performance is a strong one, 0.76. So that is partial least squares. You can see, again, this depiction of these standardized path coefficients. And again, they map on to our downstream variables this way. 0.55 and 0.57 represent the R square. So 55% of commitment is explained by these upstream variables. And then 0.57 is accounted for by the relationship from commitment. Okay, that concludes our session on correlation and regression. We've ended with a modeling technique here, partial least squares. You might see that in practice. It allows views of complexity and can be very informative to managers.